My name is Andy, and this is my colleague Thomas.
Hello, everyone.
And we're speaking to you today from EA Technology in Chester, which is in the northwest of the UK. The idea of this webinar is to highlight to people just how the Ultratech Plus instruments has moved on and how we are conscious of listening to our clients in trying to move forward with this, and to establish with those people on this webinar how much the partial discharge, basically the phase reference facility on the unit is more than just a background feature. It is now being highlighted by everyone as the way forward to give you the most notification of if partial discharge is present on your unit. I don't think that we're getting anyone else moving in at the moment, so I think we'll take it that everyone that is joining is joining. So, quick overview, partial discharge. We hope that everyone that's attending this webinar has a good awareness of it. Otherwise, I don't think you'd actually be attending this webinar. Partial discharge over the years has been recognised as one of the most serious things that needs detecting on switchgear and cables and the like, in order to give us a heads up to do preventative maintenance rather than reacting like the fire brigade and having to work to reactive situations. So the contents of the webinar we're going to try and fit in today is we're going to do an overview of PRPD, partial discharge. We're going to show you the online sensors that are now currently available, and a new item which we'll keep to the end as a big surprise. We're going to do the phase resolved partial discharge pattern, how it's created. You will notice that the acronym that seems to be adopted all the way through becomes PRPD, which is phase resolved partial discharge. What this pattern can tell us, and also we're going to refer to some case studies that have been generated by some of our colleagues, and hopefully that reference will highlight the clarity that utilising the phase resolved patterns does bring. So what is the PRPD, or the phase resolved partial discharge reference plot? It's a visual representation of partial discharge, the activity that's happening inside your equipment. But what it's doing is, by a reference to the electrical cycle, it's actually plotting the activity as it is occurring, and it's giving you a heads up to potentially what could be building up to a critical situation. And the idea is to get ahead of this and be aware of it. People are using the phase reference plot even in situations where there's nothing on the equipment. So in other words, in the green zone of our handheld instruments, because they can use that at a later date, that data, to see if anything has started at an early age to start building up. So it's not just a reference that people take just when they start getting notifications the partial discharge is present. It's also to give you a heads up of how it's starting to accelerate or build up. What I forgot to say, and I do apologise for that, is if you do have any questions, please put them into the chat room. Conscious of time that we've got allotted for this presentation, if we've got time at the end, we will come back to the questions and answer them while we're on this presentation. If not, we have booked time in the future to go back to these questions and try and answer them, and that will be made aware at the end of the presentation of the times and things like that. So what was of the first examples that we've got just on this slide is to show that this is the same location that someone took a measurement on a piece of equipment, and without the phase lock, as you can see, the correlation is just distorted, and with the phase lock, it's actually given us a decent pattern. I'm going to leave this alone because I've got my colleague Thomas here, who's obviously got a lot more skills than myself to talk through these things. The unit we're talking about with the handheld instruments, obviously just to make sure that people aren't thinking of our older instruments, is the Ultratech Plus 2. This has built into it a photo sensor which locks onto available frequencies in the substation where you're doing the survey. It also has alternative ways of locking onto it, as the E-field, and what I will do is reference how people have come back to us about this phase lock at a later time. Quick overview, some photographs of partial discharge. I think most people have actually seen these before in the past, but it's, you know, just to give people some of the instances of what can cause partial discharge. It can be either located inside or outside the equipment. The picture on the top left-hand side is showing voids, which would eventually build up into heat and also breakdown of the units. We've got all the usual signs of the surface discharge, where it's tracked on the other one of the cables, but it's not been detected at an early enough stage to stop the deterioration that it's actually leading to. Different partial discharge classifications. We've got the internal discharge, which obviously we're using the TEV sensor on the handheld unit to detect it. We've got the surface discharge, where we use the external accessories, including the onboard built-in microphone on the handheld unit. Chrome discharge, which again will be using headphones and external sensors, and we've got a discharge over the gap floating metalwork, which you can use both sensors. I'm going to show you some pictures of these in use. If the sound of surface discharge is detected with your own ears without the use of headphones, then I do suggest that it's probably at a level that you shouldn't be in that building or close to it anyway. We've got all the sound sensors, the external microphone, the parabolic dish, and the contact probe that we can all put into the handheld unit, and all of these will be generating phase reference or phase plots as long as you've locked onto the phase lock. We've got the other accessories shown at the bottom, which is obviously for your TEV sensors. You've got your actual handheld unit sensor, you've got your HFCT, and you've got your UHF directional arrow. So, how is the phase resolved partial discharge or phase reference partial discharge pattern created? And this is where I hand over to my colleague Thomas.
Okay, so before we actually discuss various types of discharges and various sources of discharges and related phase resolved patterns, it would be really good to quickly overview how the actual partial discharge pattern is created. So what we're looking at here is a graph that you probably might have seen before in various literature. So what we're looking here at is the line voltage, so VA. So that's the voltage across the healthy part of the insulation as per design, designed to take that voltage without breaking down. And we're also looking at the VC, so that's the voltage across the cavity. So that voltage across cavity will be much lower than the voltage across the healthy insulation. Obviously, the cavity is now filled with air as opposed to insulation, and that air has every chance to break down once the sufficient voltage is reached. And that voltage is highlighted in that graph as U positive, so the PD inception voltage. So the voltage at which we reach high enough volts to drive that spark, PD spark across the gap, and you can see those pulses. Every time the voltage collapses across the gap, a PD is generated, current pulse is generated as per the lower part of the screen. So you can appreciate that those occur typically on the rising positive edge of the power cycle and the rising negative edge of the power cycle. Therefore, for discharge from a source with an insulation or on the surface of the insulation, we will typically end up with two clusters of pulse distributions across the power cycle. So in the first quadrant of the sine wave and the third quadrant of the sine wave. And obviously all that will repeat every cycle. Excuse me, there we go. Next slide, please. Whenever that happens.
Was working until you do.
Well, I touched that, and that's all. That was enough. There you go. We're back. Okay, so PRPD pattern is actual display of amplitude of PD activity on vertical axis and detected by various PD sensors, as per shown example in this slide. So that could be the TEV. So internal discharge, ultrasonic, surface discharge, HFCT, etc. So those pulses, the amplitude of those signals are plotted against the phase angles, so horizontal axis, at which the PD actually occurs over time. So typically when we use UltraTEV Plus device, when we record data digitally, we typically record 10 seconds of data, which obviously then equates to 500 cycles worth of data at 50 Hertz and 600 cycles worth of data at 60 Hertz. So you can see representations of those PD pulses as the dots on the screens, and you can clearly see for different sensors there's groups of discharges separated by 180 degrees, whether you look at the TEV, ultrasonic, HFCT screen on this display. You can also see that some of the dots are of different color, and that is related to the intensity map. So how active those sites of discharge or how frequently those pulses occur. So if the pulses occur at similar positions or very close to this, the positions within cycle, per each cycle, the color will change towards red. So that's to indicate the intensity or repetition rate. So in this slide, what we try to show you is how important the correct phase lock frequency phase lock is. So the lock to the mains frequency, which, as Andrew mentioned probably before, it's primarily achieved by default by the photosensor included in the UltraTEV Plus. So on the left-hand side, we've got the absence of phase lock. So this was done on purpose. So there's a discharge side there. So both screenshots show discharge from the same source. It's the same location, same sensor was used. On the left-hand side, we've got absence of phase lock. So you can see the pulses drift to either left or right-hand side of the screen, and effectively what's created as continuous signal across the power cycle, loads of dots across the power cycle, which obviously, as we know before, has nothing to do with PD, because we mentioned PD occurs on the rising positive edge and rising negative edge of the power cycle. On the right-hand side, we've got correct phase lock, good phase lock, and you can clearly see two groups of discharges. Well, actually, what you're looking at is probably three groups, but please bear in mind that the group closer to zero crossing point actually belongs to the last group. So it's still two groups separated by 180 degrees. Okay, another example. Again, we've got on left-hand side, incomplete phase lock. So we've got a bit of a buildup of phase resolve pattern. So it looks a little bit of like PD. We can just about tell that there's some groups within this on the screenshot, but it's not very clear. So that could happen, for example, in real life situation, if we triggering of the lights and the light source is behind us, if we start casting shadow on the photosensor, the instrument might lose the phase lock. So on the right hand side, we've got complete phase lock. And that enables us to carry out a detailed analysis. And from that, we can see that we clearly have defined two sets of clusters. So one of them, the first set of clusters from one source of discharge is highlighted with the red circles, and the other cluster with the dark blue circles. So you can see that phase lock, correct phase lock, now enabled us to actually correctly analyze that there's two separate sources of discharges, probably most likely on two separate phases. So what PRPD pattern can tell us? Well, each defect, internal defect inside of the insulation, depending on the actual shape of defect, might produce different phase resolve patterns. It also depends whether the defect is closer to the conductor or screen. That will then again end up with different phase pattern. For the surface discharges, depending whether surface discharge, it's a discharge across the surface towards the ground, as in top right corner, or whether it's a discharge across the gap, that again will end up with different phase resolve patterns. Corona discharge, so bottom right corner, typically from sharp edge and high voltage, because there's only one electrode involved in that discharge. Typically, there's only one group of discharges across the power cycle. And in this screen, we've got very good examples of various types of discharges mentioned previously, and you can see, looking at them, the distribution of pulses across the power cycle, how very much different they are depending on where they actually occur. So top left corner, we've got typical internal void discharge, single phase, probably somewhere within the middle of the insulation, and because the amplitude on both halves of the power cycle is similar. And we can clearly see there's a leading edge there, which almost follows the actual sine wave as the voltage builds up, and that initial discharge occurs, and loads of pulses after the leading edge, which obviously are the after effect of the changes within the cavity. Every time discharge occurs, there's actually physical changes within the cavity of the insulation, chemical byproducts. So we start getting loads of different effects. And the discharge repeats again, probably within the same half power cycle, again within the same cavity. Okay, top right corner, this is very, very characteristic phase resolve pattern for the PD inside of the oil, whether that's a transformer, oil fluid transformer, or oil switchgear. They typically look like those clouds, clouds of discharges, very high intensity, hence the red color. So if you ever see anything like that and you're testing oil-filled acid, the likelihood is the PD actually coming from inside of the fluid insulation. Bottom left corner, typical pattern for contact of floating metalwork discharges. Those discharges tend to be similar amplitude of very, very wide inception windows. This is almost like a charging, discharging capacitor type of effect. The gap is really defined, so those discharges always discharge across set gap, and there's no void as such included there, so no after effects of the voids. So they typically end up to be very similar magnitude across the power cycle and quite wide inception windows. And the fourth and last in bottom right corner, we've got discharge, internal void discharge, probably some solid insulation type of insulation, hard insulation, epoxy resin insulation, or pitch insulation, and there's only one group, which means that discharge probably occurs either near earth or phase conductor. Okay, so we discuss internal discharges, and now we move on to ultrasonic discharges. So discharges on the surface outside of the insulation detected with ultrasonic sensor. So again, looking at those different patterns, we've got corona discharge, just one electrode, therefore just one grouping. So bottom left corner, we've got gap and contact discharge. Again, it's possible to detect those discharges with ultrasonic sensors as well, because there will be typically some earth path through which the signal will travel to the pickup, and they, again, tend to be very similar magnitude across the power cycle for all the discharges. Sometimes there's a bit of this trail off happening. On the right-hand side, top and bottom, we've got discharges, single and multi-phase discharges, and single phase discharge, as you can appreciate, clear separation, 180 degrees, and the off time when the discharge is not occurring is much longer. On the multi-phase discharge, where the discharge occurs between two phases, the inception window is much wider, so the PD happens over a wider part of the phases of cycle, because both phases are discharging at the same time. Okay, so we're going to follow up with some case studies just to discuss a bit more the analysis of the phase resolve pattern itself, and hopefully you guys can pick up how much sometimes information you can get from phase resolve patterns. So the first case study, the signals were recorded with the flexible microphones, so ultrasonics outside of the insulation, and you can see this is typical pattern for the gap, surface gap, contact gap discharge. So that was from air insulated 11 kV chamber. And if we look at the patterns, we've got this rectangular distribution of the pulses, tight clustering. So that's potentially discharges from one phase, and the other group, which is probably other phase discharging at the same time. And this is what was actually found on follow-up investigation. So you can see clearly lack of prescribed clearances between insulated conductors, and you can see there's a buildup in that middle photo. You can see buildup of the white oxides. So that will continue to build up until obviously completely bridges, and there's going to be obviously face-to-face complete discharge. Okay, so moving on, we got an example of discharge collected with TEF sensor. So internal discharge, internal to the insulation. So that was collected on air insulated 11 kV CT chamber. Obviously inside of that chamber, there will be CTs. So very typical for internal void type PD, single phase. There's only single phase discharge here. So defect probably somewhere halfway through the solid insulation. So we've got very well-defined leading edge. So that initial discharge, it's defined almost by the actual characteristic geometrics of the actual void itself. So that initially discharges created quite a high level of PD. And what follows up after that initial leading edge is that more sparse clustering of the signals, and this is typically the after effects, the semiconductor effects, and all the gas byproducts within the cavity after the initial discharge create perfect environment for more discharges to still occur on the rising or edge of the sine wave, or falling edge of the sine, rising falling edge of the sine wave. And this is the actual source of discharge. So it was from CTs. This is a gear that some of you might be familiar with. So that's railroad T, if I'm not mistaken. CTs from railroad gear. That gear was obviously used a lot in the past. And you can see on the right-hand side the CT that actually failed in service, but discharges actually occur within the insulation, solid insulation, hard insulation of that. Another case study, it's a very interesting one. So single phase discharges, very well defined clustering events 180 degrees apart, but looking at the actual phase resolve pattern, you can probably appreciate there are multiple sites of discharges, because we have multiple leading edges. So that'll be the first group of those leading edges, second one, third one, fourth one, and finally the fifth one. So very typical for hard insulation, epoxy resin type of pitch-filled insulation, those wave fronts. And what we also have is that loose clustering of the events after the initial discharge on each of those cavities. And those discharges, all of those were detected in 11 kV pitch-filled insulation. Sometimes over time, this pitch could shift a little bit, creating gaps and voids, hence the discharges. Next case study is case study from TEF, with TEF sensor as well. So indication of internal discharge. Again, it's a pitch-filled 11 kV chamber, and there's a lot of things actually happening here on that screen. So we've got at least 4 sources of internal PD suspected on different phases as well. So the first most obvious would be that group highlighted here with the red circles. So it's quite high magnitude discharge, and you can see it's very much different to another group. So you can see now clearly there's an offset between the red and there's a phase offset between red and green group, which obviously indicates that those discharges actually occur on separate phases. There's another group here present. So all of those groups have similar magnitudes on both sides of the both halves of the power cycle, indicating that it's occurred probably somewhere in the middle of the insulation. And finally, maybe not so clear, there's a 4th group here, and that's leading edge there, and there's only one. There's no corresponding leading edge on the other side of the power cycle, which potentially indicates that this is the discharge which actually occurs closer to one of the conductors in the screen on Earth. So as you can see, a lot of things going on this one slide screen. And the reason, obviously, we managed to capture that so clearly with so much detail is because the phase reference was correct, and the instrument was triggering correctly of the mains frequency. If there would be any drift to the left or right, that data obviously could look completely different, and we probably couldn't be able to pick up that many details from this measurement. So that again originated within 11 kV pitch insulation cable box, so solid insulation. Another case study is from oil-filled 11 kV transformer. We presented you before typical patterns for PD in oil, and we mentioned it's quite intense. So there's a lot of different colors here, red colors coming into play. So quite high intensity. You can see that there's almost 20 pulses per power cycle. So the discharges in oil gear tend to be very intensive. There's cloud shape, and that was found to be faulty or discharging tap changer. So the issue was with tap changer. So after the initial testing of the transformer, there was a follow-up review of the DGA analysis, which is always a very good idea whenever you find any issues on oil-filled gear, to follow up with the DGA, and that indicated problems within tap changer. Okay, the last case study for today I wanted to present is a case study with the use of flexible microphone. So it's obviously discharge. Well, it's actually not discharge. This case study shows us the noise from the compact fluorescent light bulb. But the reason why it's so interesting, because you can see it does follow the pattern. So you could almost tell there's a phase result pattern there. Almost like a phase result pattern of PD, because there's clear separation between the groups of the events, where you can see those are built up from loads of individual clustering of the signals. So the reason why it builds up the patterns, because obviously what it is, it's a light bulb that operates at 50 or 60 hertz. So it will follow up the mains frequency. It's powered by mains, but the sound of it is completely different. It's almost like a high pitch transformer buzzing, and the repetition rate will be definitely different to the actual PD, as well as the fact primarily it's built up on loads of different clusters of the events. Okay. Hopefully that convinces you how much you can actually get from a phase result pattern, how much information if you analyze it correctly, and obviously how important is the correct triggering. Without that correct triggering phase reference log, we wouldn't be able to pick up that many details from any of those case studies and phase result patterns presented. I'll hand over to Andrew now. He's probably had enough of PD.
Take a breath. Thanks, Thomas. Yeah, I think everyone probably found that interesting, but yeah, so many references, so many things. I think what this has proven to everyone, the PRPD or the phase reference partial discharge plots have come to the future. What we've done is, over the recent years, we've been using the phase lock facility, but not realizing that the phase lock facility, how useful it is. And now it's become right to the forefront of what everyone wants, to make a more concise and clear definition of any partial discharge that is present in their equipment. So listening to this, we've realized that a properly phase locked PRPD pattern can actually almost make the definition of the partial discharge a really reliable analysis can take place. And also, not just in detecting this, it can also rule out anything that has given us false references. So with this in mind, EA Technology have moved forward and taken note of a lot of clients regarding this. And what we have done is we have actually developed something that will give a more concise phase reference lock on inside certain situations. One of the criticisms that I think you mentioned earlier, Thomas, was that sometimes you can block the optical sensor out on the handheld unit, and what with this in discussion, a lot of people have actually highlighted is the fact that they'd like some way of being able to lock onto the phase reference more as a concise and clear signal. And with this in mind, what we've done is we've developed this unit that can do a wireless phase lock inside a substation. It can either run at the 50 hertz or the 60 hertz cycle, depending on obviously your location, which country you're in, and it communicates directly with the handheld unit to give it a more concise and locked on feature. Saves losing the phase reference when it is taking details into it and actually producing the phase lock plot. So yeah, really impressed with this. This has been trialed out, and the benefit of it has been proven, and this is why obviously we've taken it forward into this new unit. Apologies for this, but Thomas is looking at one of the questions that we've actually been sent in. So the new phase reference accessory, obviously it's the benefits it's got wireless design, you've got no cables, you can actually plug this in so it can be charging as well while you're utilizing it to carry out your surveys. If that isn't a facility, it's got a really long battery life, as you can see on the slide, it's saying 16-hour battery life. You know, it is an IP42 rated enclosure. We're going to give you the opportunity, if you are interested in purchasing this, which to be perfectly honest, why wouldn't you, to contact us at the sales, and we can give you more details going forward on this. I did reference it a little bit earlier, must reference the work that our colleagues in Australia have put into taking this product forward, and you know, that is acknowledged. Thank you very much. I'm just going over now. We're going to try and see if we can deal with any of the questions that need to be verbally, as Thomas is dealing with them at the moment. I think he's dealing with directly answering them back to the people. What I did explain at the beginning is that we are coming virtually towards the end of our time for this session. So rather than get involved in a big Q&A answer session, we have also arranged for some later in the future that we can go on and answer the questions that you've sent in, or we can arrange, if you make contact with us, to actually get involved in the direct questions that you want us answering to yourselves. I think, to be perfectly honest, after all the case studies that Thomas has presented, I think that everyone realises that these PRPD, these phase resolved partial discharge plots, are the way forward to give clarity, to give everyone a more defined way of answering, do I have partial discharge present in my equipment? Why wouldn't you want to be able to take a screenshot and show the representation to any external clients that you're working for, or even to people within your own company, of why you need to address any situations where this could be present before it becomes a critical moment where you have to react to it without any planning. Just to round off, coming towards the end of this presentation, if anyone feels that they need to get more involved in discussions, or if they feel that they need training within partial discharge, we at EA Technology do carry out a number of different courses. I'm not trying to reference other things that are there available at the time, but the partial discharge course will also go through the analysis and interpretation of any data collected with your handheld instruments. Please feel free to contact us directly for any further discussions that you may need for any training. I do suggest that you potentially go onto our website and have a look at all the different courses are available. And all we're trying to do is, with these courses, pass on the training that's been gained over the years by EA Technology and their staff and their experts, and pass that on to people, and then therefore hopefully it instills a safe working culture for people. Partial discharge has come to the front and is one of the most referenced events that causes failure with equipment, and hence why it has come to the forefront. I'm going to just request anything further you want to add, Thomas?
No.
Well, on that note, I think that I would like to say thank you to Thomas. Thank you for everyone that's attended. Yeah, really do appreciate your attendance, and hopefully we can talk to you in the future about anything you require, and hopefully you will consider the new phase reference equipment that we've developed. Thank you for your time.
Thank you.